So, this week's class we have discussed a lot of theory. So, let us now go back to doing our practical calculation. So, one of the first calculation we will do this week is the proton affinity of methyl anion. Because proton does not have any electron, so it will be same as the electronic energy difference between the methyl anion and methane, and of course, we are still not know how to do geometry optimization. So, we have provided the optimized geometry of methane and methyl anion at B3LIP def2 QZVP basis set, and we need to calculate the proton affinity at Hartree-Fock PBE B3LIP M062X MP2 using def2 QZVP basis set. So, the acceptable value of the proton affinity is 1785 kilojoule per mole, which is obtained from some accurate high level wave function based calculation. So, now let us start making our input file. We know that for doing this kind of calculation, one should create an Excel file. So, let me create a blank Excel file, and here I write the method. This is the methane energy. Methane should be written as H capital. And this is CH3 minus energy, and this is proton affinity, and this I will calculate in kilojoule per mole. Do not forget to write the acceptable value, and that was 1785. And let me save it. Want to see this PC. I want to see it. Let me create a new folder called week 6. And let us be. Okay, so this is written. Now let us run our calculation. Let us go to Notepad. Okay, let us make an input file by hand. So the first functional we should use, Hartree-Fock def2 QZVP Rij cos x zero 1 and let me copy the coordinate of methane. And let me save as files. I need to go to NPTEL week 6 ch4hf.inp. Okay, I have not given the star below, so let me give it and save it. Now I go to NPTEL week 6, I open in terminal, increase the front a little bit, ch4hf.inp, So by the time my calculation is running, I can just change the charge here and let me copy the CH3 minus geometry. I hope I have copied it. Yes. CH3M dot CH3M Hatry-Fock. Files. Okay, let me run the calculation. Orca CH3M INP let me open the output file. I go and copy the final energy. Now my anion is also done. I go to the end and take this energy. Oh, I did a mistake actually. I should have so I should have put it in the next line, and now I should calculate the proton affinity. So it's this minus this. Don't forget we have to convert into kilojoule per mole. The conversion factor is 1 AU. 1 AU is 2625 point big number. Let me copy it. So the Hatry-Fock, the energy is coming 1843.717. So it's actually there is a considerable difference. Now let us go to the other functionals. So let me close both of this. I can actually edit this one to make it a PBE. So the next functional we have been told to will try is the PBE. So I save as CH3M PBE, all file, of course I have to modify it. So now I will write it PBE. For PBE I don't need Rij cos x, just Ri is fine. So let me run the calculation. Orca CH3MF HPBE. I can also copy the CH4 Hartree Fock and I can make it a PBE. Rij cos x I don't Rij cos x I don't need. So it's CH4 by the time it's running, let me open the output file just to show you certain things. So it says the basis set, it uses the split Rij to do the calculation, it does not use any range separation. And this is something interesting is DFT grid. We will do a separate discussion on how the grid, what grids are and how the result depends upon grid. So this is how the function is. If you look at it carefully, you can find out what are the parameters x kappa, what is the exchange parameter is PBE, and it says what is the LDA part, what is the GGA part. So it's PW 91 LDA, then you have a GGA part. And of course, you solve it like a Hartree Fock, that is why it is given. So, see there is no explicit Hartree Fock exchange. So, it is written how much is the, there is only a correlation part. There must be somewhere a description of the what kind of normal DFT exchange is there. This is only here only. So, there is no Hartree Fock exchange here, and the individual terms, exchange correlation term, the initial with the initial guess, this is given, and the calculation is done. After the calculation is done, it is actually very similar to what it is in the case of Hartree Fock. One thing to remember is that in the case of DFT, this HOMO and LUMO, only the HOMO and LUMO can have some physical significance in due to the so called Zonach's theorem. It is like equivalent to the Koopman theorem in the case of Hartree Fock. So, you can actually write the IP as a negative of the occupied orbital energy and the EA as the negative of the virtual energy. The thing is, for the other orbital there is no physical significance. Remember why these orbitals were brought in. So, these were brought in to fit on my kinetic energy. This kinetic energy was something which you cannot write in terms of only density in the Hartree Fock Kohn-Sham in the exactly. And so, in the Kohn-Sham picture, what you do, you bring out this orbital to do the fictitious to fit this to this fictitious orbital to fit the kinetic energy part. It does not correspond to what is the case in the Hartree Fock, where this orbital gives you the wave function corresponding to the minimum energy in the single determinant picture. In the case of DFT, there is nothing, no such variational theorem is available in the case of approximate DFTs. So, that means this orbital except HOMO and LUMO actually does not have any physical significance. So, when you plot the DFT orbital other than HOMO and LUMO and try to get some physical interpretation out of it, always remember you are doing it considering that it is similar to an Hartree Fock determinant and Hartree Fock wave function. In actually they do not have any physical significance. I thought it might be interesting to discuss this one. Okay, so this is my single point energy. Let me copy it. This I write as PBE. and I also need to get the CH4 PB energy. The minus sign I forgot to put while copying. I did not put the minus sign. So, after putting the gradient corrected functional, you see the proton affinity is slightly improved. So, it is slightly better than what you will get from a Hartree-Fock calculation. Now, let us check B3LIP and the other one, so the GGA hybrid B3LIP and meta GGA hybrid MO062X. So, quickly let us run the calculation for B3LIP. Again I can this is Rij cos x, because B3LIP, remember, it has an Hartree-Fock exchange component. So, to speed up the exchange, it cannot be done with only Ri. So, I have to use Rij cos x. CH4 B3LIP I am not given the input extension. So, by the time it runs, I make the input file for the anion also. CH3M B3LIP dot INP you see one thing, that actually the hybrid functional calculation actually taking longer time than what we will see from a normal PB calculation, because remember there is now a Hartree-Fock exchange is there, and it is slightly actually more time consuming than a normal Hartree-Fock calculation. Okay, so this is done, but let me submit the CH3M B3LIP file and then we will see the output file. Let us first go to the end. It taken 1 minute 15 seconds, whereas if I take CH4 PB, it has taken only 14 seconds. If I decide to open the CH4 Hartree-Fock, I believe this one, it is taken 17 seconds. So, PB is the fastest because it does not have any Hartree-Fock exchange, and in the Ri it can be factorized 10 to the power 3. Hartree-Fock comes next, and the DFT is actually the slowest among all the 3 methods. Now, let me get the energy. So, it is B3 lip. That is why I am starting it seeing it from the top, because you see here I forgot to change the PB here. So, this type of mistake can happen while doing calculations. So, it is always a good idea to open your output file and read at least the first few lines and see if you have the same input file what you intend it to have. So, let me save it again. And run it again. What is the problem? Okay, I have not given Rij cos x. So, let it get run, and I will give a homework problem. To perform the M062X and MP2. So, this I will not do it in the class, you have to practice it yourself and you have to let me know what is your interpretation of the results. So, the calculations are still running. By the time my calculation is running, let me go back at my CH4 B3 lip dot out. So, because it has an Hartree-Fock exchange, it has the cos x grid settings. So, now you see the thing. So, exchange functional is B86 is the DFT exchange, correlation function is lip, LDA part of the GGA correlation, that is VWN5, whereas in the case of Gaussian it is used VWN3. That is why the B3 lip and B3 lip G is different, and how much is the Hartree-Fock exchange is used is 0.20 and rest of them is the DFT exchange, rest of the output file is same. So, let me get the energy. So, from going to PB, the B3 lip, the values have slightly deteriorated. Of course, the values are still much better than the Hartree-Fock. It will be interesting to see how the M06X2 and MP2 values are there. So, this will be your homework problem for this week.